Welcome back to Nature in Code. We're in chapter 3, and we just developed a visualization of genetic drift in the browser. And we just finished a discussion about the idea of an array, which is basically a set of elements or a list of elements, if you will, a vector of elements in JavaScript. And we're going to use that now in order to produce a visualization of not just one simulation, but multiple simulations at the same time. And so if you look at our current code, we are storing all the allele frequencies that we calculate in each generation in this data array. So we're pushing P here into the data array that we initialized here as an empty array. And then we run this one simulation and we push each new data point into data, and then at the end we pass this data array to the draw a line chart function, which then goes and plots the data like this here in this fashion as a line. What we would like to do now is we would like to run this exact same thing multiple times. So let's say we want to run this 10 times. So what we need is a way for our data array to not just contain the results of one single simulation, which could each be 1,000 generations, but of 10 simulations. And so that's going to be a two-dimensional array, and then we're going to pass that two-dimensional array here to the drawing function, and I've written this function in such a way that it can handle two-dimensional arrays. So let me just clarify this concept here on the drawing board. So right now we have our data array, and it's an array that has multiple elements of a simulation. So there might be 0.49 and then 0.48 and 0.485 and so on. However many generations this simulation runs. So the data array at the moment contains 1,000 data points or 1,000 elements representing one simulation, right? However, what I would like now is for the data array to be a two-dimensional array, where rather than having all these elements in the array, these 1,000 data points, I want it to have 10 arrays. Okay, so the elements of this data array are going to be arrays and so on. Okay, 10 times 10 arrays. And each of these arrays now is what data used to be before. So each of these is 0.49, 0.47 or whatever the values are going to be. So each of these is going to be 1,000 data points, and each of these is going to represent one simulation. And so the data array will essentially contain 10 arrays, which each contain these 1,000 values for each simulation. All right, so how are we going to do this in code? Well, if you look at this code, basically the simulation is this, right? This says, well, for however many generations, at the moment 1,000, call this next generation function and calculate the next, or simulate rather, the next generation A1 allele frequency. So I would like to do this 10 times, and of course I'm not going to just take this and copy it 10 times. We've learned that that's a bad way to do it. But what I'm actually going to do instead is I'm going to wrap this into a function, and I'm going to call this function simulation. Okay, so this whole thing here will be wrapped into a function. And I'm going to call this simulation. And now I'm going to call this function 10 times. And again, I'm not going to write simulation, simulation, and so on. That would be silly. I'm just going to create another for loop, right? Just like before. I is smaller than 10. I want to do this 10 times. And then, of course, increase the counter, this I, to avoid an infinite loop. And now I'm going to call simulation in here. So this is going to call simulation 10 times. All right, almost there. So what about the data? At the moment, we're just pushing the data into this array. And so now we would just have an array with 10,000 elements at the end of after this code is executed. And that's not what we want, right? We want to tell this function here, hey, push it into the specific subarray of the current simulation. So I want our function next generation not to worry about this at all. I'm basically just going to say, you know what, I'm going to pass the relevant array as a parameter to next generation. And then I'm just going to push the value into that, and I'll leave it up to whoever calls next generation to actually pass the correct subarray. So I'm going to assume here that I'm going to receive as a parameter an array, and I'm going to call that simulation data, just so that it has another name. And then we really want this p-value here to be pushed into that array. And now basically this function says here, you know, I'm completely oblivious about where I need to push this. You're just going to hand me an array, and I'm going to push it into that array. But you, whoever calls this function, needs to be sure to pass me the correct array. And of course, that just needs to be the corresponding array of the simulation. So if we run the first simulation, it has to be the first subarray of data. And if it's the second simulation, it has to be the second subarray, and so on. So where do we know which simulation we're currently running? Well, down here. Down here we know it. Because this is actually our simulation counter, if you will. I going from 0 to 10. And so I'm just going to pass here I to the simulation function, because the simulation function itself calls next generation. So simulation will pass this value. I'm going to receive it up here as a parameter. I'm going to call it simulation counter. And now here in simulation, I know, thanks to this simulation counter that was passed to me from simulation, I know which simulation I'm currently at. So I can pass on the correct subarray, which will be data at the index simulation counter. Okay, so if we're running this the first time, I will be 0. I'm going to pass this over here. So simulation counter will be the value 0. So data 0 will, of course, be the first subarray in data. So there's one thing missing, therefore. I'm talking about these subarrays, but I actually haven't generated them yet. So whenever we start a new simulation, we're going to push an empty array into this data array. And so now we know exactly which array we're talking about here. The corresponding array that was just created here, and we're going to pass that to next generation, and next generation will push it into the corresponding subarray. So let me save this, and let me go over here to the browser and reload this page. So something interesting is happening here. This is not correct yet, and this is not correct on purpose, because I've made a mistake on purpose that is very easy to make. So if you look at this graph, there seem to be other colors, other lines, but they're flat. Let's reload this. Yeah, this is actually a good example. So you can see there's a second line up here, or maybe it's not the perfect example yet. Let's use this. So we start with the blue line is the first simulation. It starts at 0.5, and then it starts fluctuating, and then it ends here somewhere between 0.6 and 0.7. The second simulation actually starts here where the other one ended, at 0.6, 0.7. Then it goes to fixation, and then all the other simulations start here up at 1. That's not what we want, right? We want each simulation to start at p.5. And you might say, well, why doesn't this work? Because didn't we define p to be equal to 0.5? Yes, we did at the beginning. But then, right, p gets overwritten here all the time. and we actually never reset it to 0.5. And we have to do that, of course, before we start a new simulation. So here, before we start a new simulation, we're going to set p back to 0.5. Now be careful, and this is where the issue of scope comes in that we talked about in an earlier video in chapter 2. Don't say var p equals 0.5. Because if you do that, save it, reload, you still have the same problem. And why is that? It's because var p means you're not creating a local variable p that's only valid here in this function, and but next generation doesn't care about this particular p. This p here is only valid in this function, and we don't want that. You want to overwrite the global p here, the one that we defined up here in the global scope. So don't say var p, say p equals 0.5 because you're overwriting a variable here. You don't want to create a new one. And if you save this and go over to the browser and reload, now you can see it works. Okay, that's great. Now, just a few small things I'd like to fix here. So one thing I don't particularly like is to hard code numerical values here in a loop. So I'm just going to replace this 10 here with a variable that I'm going to call simulations. And I'm going to save simulations up here, simulations. And the other thing that I think is a little bit useless is you're overriding here 0.5 at all times anyways when you start the simulation. So it's not necessary actually here to define it or to initialize it at this value. So you can also just define the variable as p and not assign it a value, because it will be, the first time it will be used, it will be assigned a value anyways. And you could, of course, also save this value in another variable, say initial p, and define this up here if you wanted to. But I'm just going to leave it at that. I'm going to save it and still see if this works. No, I introduced a mistake somewhere. Let's see what I've done. Oh, I set it to 0. Yeah, that's not quite smart. It should be 10. Okay, so it works. It ran 0 simulations. So let's reload it. Okay, still works. Now that we have this code in place, let's investigate a little bit what happens here with drift as a sort of a dependence on the population size. Let's set these values here to 200, okay? 200 generations and a population size of 200 individuals. Save and go back. All right, so you can see here that these allele frequencies are fluctuating pretty substantially, and in fact so hard that some of these simulations have even lost all genetic variation. They've lost, so this particular one here has lost the A1 allele completely and therefore lost all genetic variation. If we reload this, oh, here actually, let's see, 4 simulations out of 10 that have lost all genetic variation. These two here lost the A2 allele, and these two down here lost the A1 allele, and so on. So let me go back to the code and now reduce the population size by a factor of 10 to 20. So let's save this and let's reload this here in the browser. And so you can see here quite dramatic difference. Practically all simulations will have lost the genetic variants. One of the alleles will have gone to fixation. There's maybe occasionally a single simulation run where both alleles survive the 200 generations. Hasn't happened so far. It might eventually occur, but it's, as you can see, it's a rare thing, and you basically have to expect that genetic variation here in this case is reduced and completely lost, or gone to its minimum value by somewhere between generation 100 and 200. So quite a dramatic outcome. Let's do the opposite here. Let's actually, starting from 200, let's increase the population size by factor 10. Let's save this and go over here. And this, again, is, of course, a completely different outcome. The allele frequencies here are still drifting around, and the drift seems to become stronger, so the effects, of course, add up over time. However, this effect, of course, now is much more muted compared to the smaller population size. And this basically just confirms our intuition that we developed with the coin flipping. If you flip just a few coins, you can have quite dramatic outcomes. However, if you flip many, many coins, or you flip a coin many times, the effect of random chance is going to be much smaller on average. And of course, that is just a question of time here. So we're running this now for 200 generations. If you run this for 2,000 generations instead, just give it a little time, then yes, of course, you're going to see the exact same thing. Those will eventually, the simulation runs will eventually go to a situation where one of the allele fixes. And actually, let's do a little experiment. Let's do this. Let's up this to 20,000. This will take a few seconds here in my browser, but it should just be a few seconds. And here you can see now, also with a population size of 2,000, given enough time, all of these simulations will go to fixation. One of the alleles will go to fixation. Let me reload this again. Yeah, even faster here in this case. So it's all a matter of time. It doesn't matter what your population size is if it's not infinite. In other words, if it's finite and you give it enough time and there are no other processes, then these simulations suggest that your genetic variation will be gone after some time. And the smaller the population, the sooner that's going to happen. And so what I would like to do in the next video is to develop some mathematical, more quantitative intuition for this phenomenon. But I think we've gotten pretty far here. We've developed a stochastic simulation of genetic drift. Let me reload this here. We plotted the simulation results in the browser using a JavaScript library. And that's pretty stunning. Congratulations if you made it this far. So I'll see you in the next video.